And then what does the sigma notation mean? It means everywhere put a plus sign in between. All right, so if you write this out or expand everything, it would be this. And then square all the terms, add them together, you get 271. There were no tricks here. Hopefully this was kind of a free problem. All right, first on top got 271. I'll assume everything we need this to do. All right, any questions on that? So our main goal, why do we want to be able to do this? Before we did, like you would do difference quotients where you'd move things closer to closer and you take a limit. Now our goal is can we add a bunch of things together? But if you're going to add a bunch of things together, you definitely don't want to write out every term and add them, right? That would be awful, right? So really the goal is to just introduce this notation. How to write this in shorthand. So in general, somebody said it's a for loop, which is true. It's basically like expanding out a for loop, writing all the steps. So if you're science. So sigma notation. Let's say we have a bunch of terms indexed by k. So k is like our independent variable. It's the number we're plugging in. And what this says is the range goes from m to n, counting every whole number in between. All right, so this says if I start at k equal m, the first term is just am. And then increase the index by 1, add the next term. And this list could be anything, right? Ideally, there's a pattern, or it could just be a whole list and we know what the list is, and it's a short way to write it. When do we stop? We keep adding 1 to the index until we get to n. And then that would be our last term. All right? So it's a way to add several numbers together quickly. The other goal is, can we use this notation to write something that's simple? So let's say we had this list of numbers we're adding together. What's the pattern? What happens in the numerator? I just add 1 every time. So how many terms do I have? 7 terms. So like the easiest way for the pattern would say start at index 1 into index 7 and just count them off 1 through 7. So that's what this part says. Going from k equal 1 to 7, the numerator is just k. Every time it gets updated by 1. What's the pattern in the base?
That's all perfect squares.
They're all perfect squares. You're going to get to where you really recognize perfect squares, factorials, things like that. So they're all perfect squares, but where do I start? 4 is 2 squared. So I need to start at index 2, which is a mismatch with the top, right? The top we said would make more sense to start at k equal 1. So then how do I fix that in the base? So this would be 2 squared, 3 squared, 4 squared. So it is just increasing 1 each time we squaring it. But to start at 2, add k equal 1, how do I get 2 here? Add 1 to it. Here I need index 3. If I have index 2, just add 1 to it. So the base would be k plus 1 squared. So that's if we start at index 1. What else could we do? What if I really like the idea of just k squared in the bottom?
Subtract 1 from the top and then
Yeah. I could keep the bottom as k squared, but if I do that, where do I need to start? I need my first index to be 2, my last index to be 8. So then what happens in the top? I have to subtract 1 each time from the index. So those are the exact same sums. There are multiple ways to write these. Usually we decide we always want to start at 0 or we always want to start at 1, unless there's some good reason to start at a different index. All right. How can you do your science? Your for loop, you usually start at what, 0 or 1? Basically, you can think of this as you're storing part of an array, and then you're just adding the elements together. So the index is exactly the index of the array if you're in computer science. All right. So there's 4 formulas that you do not need to memorize. We will give them to you on every quiz or test where you need these. I noticed that in the reflections, people were thrilled that they had more random formulas. You don't need to memorize these, okay? So we know a few of these. So actually I'm gonna write out these two. But we know some of these just as formulas. Why is this useful? When I say add up k equal 1 to n of the number k, do you know what that is off the top of your head? Like what is that? 1 plus 2 plus 3 plus 4 plus 5, stop when you get to n. And you figure all that out, let's say n is 10, you figure all that out, and I say, never mind, make n equal 100. Do you really want to go back and do that? So you want to type it in every time? If you have a computer, you just write computer code and it does it, and you change like 2 lines. So that's cheating because it would do it all for you quickly. But let's say you don't have that. What else is useful? These are formulas that say, give me any stopping point in, this is the value of the sum. So if I said add up from 1 to 10, I can just plug 10 in here and I know exactly what that value is. And we can do it for k squared or k cubed. So we know these formulas where if you're given this sum on the left, instead of adding all these together, we've already done all the work, we know the value, it's always this output. The problem is you have to start at k equal 1. All right, what if you start at k equal 0? That's a bad question. You get the same thing unless it's the first one. Because 0, 0 squared, 0 cubed, you're not adding anything. But you always want to make sure when you do these, they assume you're starting at index 1 and the index n. Right. So I want to derive the first two. So how can we do that? So this one's like a free one. Why is this equal to n? What does that literally mean to do?
And n number of ones to each other.
What's my list of numbers? It's always the number 1. So I'm just going to keep adding the number 1. So this literally says for k equal 1, take the number 1, then add for k equal 2, my value is 1. And I keep doing that until I get to k equal n. So I'm just adding the number 1 over and over. What is that equal to? How many times do I list the number 1?
In amount of times.
N times. So I'm adding the number 1 to itself n times. So that's really just the same as n times 1. So I get the number n. Or you can think of it as counting. K equal 1, I get 1. When I do k equal 2, 1 plus 1 is 2. Plus 1, I get 3. It just matches the index every time. Right. So this one is equal to n. Please don't get your calculator on the test and say 1 plus 1 plus 1 plus 1 plus 1. You know this one. All right. This one's a little harder. This one has a cool trick to it. So this is equal to what? 1 plus 2 plus 3 plus 4. Keep going. Plus n minus 2 plus n minus 1 plus n. And we just keep adding all these together. Unless you've really read the book well or seen this trick. If you look at that, that looks like if I tell you n is equal to 1,000,000 or something, you pay me because then you take out your calculator and type 1 plus 2 plus 3 plus 4. That would be all for 2, right? So how can we come up with a formula for this? There's always weird things that happen in math. Looking at this, I have no idea what that value is. But what's strange is I can easily find what twice that value is. Kind of strange, right? That's equal to some number, I don't know what it is, but I can actually find that number times 2 pretty easily. And that's kind of the trick to doing it. So let's say I did this again. Except this time, this is kind of tricky, or bad form. It would work in computer science. This says start at 1 and go down to n. Or start at n, go down to 1. Basically, I want to write this in reverse order. So, technically, I'm saying this. But now I'm going to reverse everything. So when I write it, I want to do n plus n minus 1 plus n minus 2. Keep going, plus 3 plus 2 plus 1. Is that the second answer? When you add numbers, are you allowed to reverse the order? Yes, as long as you're not doing limits. Technically, if you're adding infinitely many numbers together, you're not allowed to just switch the order around. It makes a difference. But if you just have a list of numbers and all you want to do is add, if it's a finite list, you can add it in any order whatsoever. Yes?
So does it actually matter then?
Huh?
So does it matter then, like, which way it's written? Like, yeah, if it's
Technically,
written...
the way your book is saying things, you're not allowed to do this. Because you always add 1 every time. If you're thinking computer science, something like that would make perfect sense. Could you just write your for loop and say, go minus 1 every time? So, technically, I could write this. It's the same as this, but I'm allowed to reverse the order. So if I ignore this part, which is kind of the explanation, this is equivalence. That would be valid. Okay. Why would I do that? Now I want to, this is the major trick, take these two values and add them together. What would happen? So, this is some number, right? It's whatever this number is. It depends on the number n. I don't really know what this value is, but it's some number. So this plus this, I just get 2 times the same thing, right? What happens on the other side? I do this plus this. I get n plus 1. What if I do this plus this? I also get n plus 1. N minus 1, add 2, I get n plus 1. What about this one? 3 plus n minus 2. Be n minus 2 plus 3, I get n plus 1. What about here? N minus 2 plus 3. I get n plus 1. N minus 1 plus 2. I get n plus 1. And then this last one, I again get n plus 1. By pairing them off, when I add them together, I always get the same value, n plus 1. Why is that relevant? How many of those are there? I'm always adding the same number every time, right? So if you add the same number every time, that's the same as asking how many do I have, just multiply. So how many are there? N of these? When I listed them off, it was 1 through n, so they're exactly n of them. So I have this value added together n times. So I'll get n times n plus 1. So what did that find? When I added on the left, I got 2 of this value. When I added on the right, I got this. Now what can I do? What was my whole goal? You always forget what the goal is in that. By the time we get to the answer, we forgot what we were trying to answer. to find out what is this value, right? Now I can solve for it. And just divide by 2. So this value is exactly n times n plus 1 divided by 2. I think Euler came up with that several hundred years ago. It's a cool trick, right? It's weird. It's really hard to find the number we want, but we just double it, suddenly there's an easy way to come up with it. You are not expected to know this trick and just memorize it and do it on a test or anything like that. We will give you the formulas. But it has some good talking points on, if you're adding finitely many numbers, you can always change the order for that. That is fine. All right, and how some of this, it's all buried in this notation, but it all works together. Yes?
So if k is not equal to 1, that doesn't work.
Right. So, it's a good question. What if I had, find the sum k equal 2 to n of k? What would I do?
Would you have to subtract n from 2?
Yes. I only know formulas starting with k equal 1. So I would say that is the same as starting at k equal 1. But then I need to subtract 1. Why am I subtracting 1? That's the value when I plug in k equal 1. Actually, this is better. Let's start at 3. Then what would I do? I would subtract the sum k equal 1 to 2. Does that make sense? I want to start at index 3. So start at index 1, but then subtract everything that came before index 3. Why would I do that? What is this value? This is now the n times n plus 1 over 2. And what is this equal to? 1 plus 2. So it would be the number I know based on starting at 1 and then subtract 3. It's like we know one thing, but there are ways to work around it and find others. But then it becomes more of a puzzle. All these are a little bit puzzle-like once you start changing bounds or asking slightly different questions. Yes?
What if you have similar form to like with the k, but except it's like k minus 3 or something? Like, and then you're trying, like with the, like same idea, it's just instead of k, it's k minus 3 or something.
K minus 3?
Like,
All right, so let's do another example that I had planned, which will be similar to that, but much harder. All right, any questions so far? So I noticed a change in the notes and videos. I was involved with the first 3 units, and then I was on paternity leave when they made the 4th unit. So they don't have the same people making them anymore. All right, so let's do this example. Let's find the sum from k from 2 to n of k cubed plus 1 divided by, divided by 3. Is this similar enough to what you're? If we end up rewriting, it'll be a similar thing. So, despite the fact I've erased the formulas, we know a formula for k cubed, we know a formula for 1, but they all require starting at k equal 1. What should I do here? Yeah, how do I get to know formulas? So there's a few properties. One, all my formulas basically look more like the numerator, right? You divide all these by 3. I'll mention why this works and then we'll do it. That's like adding all these numbers together, but I can factor out a 1/3, right? So what does that mean? Anytime you have a sum, I can factor out a constant. Does it make sense? I can factor out a constant. If every term has the same constant in it, you can factor it out, right? The big thing is I can't factor out anything with k, because k is changing on every one of these. But just a number like 1/3, I can move it outside the sum. Kind of like when you did limits, you couldn't move an x outside the limit, but you can move a number outside the limit. For derivatives, you can bring the constant multiple out, but you couldn't bring a factor of x or anything out, you would need a product rule. Alright, now what?
You'd have to change the K to K1.
Yeah, really want to start at index 1. How can I do that?
-1 on the outside.
I'll do the easier way and then we can talk about another way to do it. The easier one would be, say, just start at 1. Now, can I randomly just start at the index 1?
-1.
If I do that, I added an extra term here, right? So it's almost, the way you think of it is, what if I start at 1? If I start at 1, I get 1 cubed plus 1. So put all these together and then subtract that part off. So if I start at x1, what do I need to subtract? I need to subtract the number 2. Are those now the same value? Now what? There's another great property we haven't mentioned. What can I do here? This is k cubed plus 1. I can treat that as k cubed plus, and then do the sum of the sum. Instead of writing as k cubed plus 1, I can break this into 2 separate sums. That's one of the properties we had. Instead of adding them together on the inside, add them together on the outside. So add up all the k cubes, add up all the 1s, and treat them as 2 separate summations. Does it make sense? I'm allowed to do that. This is just a long list of numbers being added together, right? So take all the numbers that were based on k cubed, add those together first. Take all the numbers based on this term, add those together second. So I'm just kind of rewriting what this order was. I can write them both the same way. Now what can I do? Why did I work to get it in this form?
Rewrite first and second terms as one form.
These are the two, if you remember, I have formulas for these two. So what are these formulas? Again, you don't have to memorize them, we'll give them to you. For k cubed, it's n squared times n plus 1 squared divided by 4. What about this one? Add number 1 together every time you get n. And then subtract 2. So our goal is always, can we make it look like one of these formulas and then plug the formulas in? I might have to kind of rearrange terms to get it there, but eventually, once it looks like these formulas, I actually know the rest. I don't have to add everything together because the formula tells me what it would add up to. So as the last part of this, what if I ask you to find this value?
You plug 100 into the pin and that file.
Yeah, take this value and just plug in n equal 100. So it'd be whatever I just got. Then I plug in n equal 100. So 1/3 times 100 squared, 101 squared, divided by 4, plus 100 minus 2. And you'd get 8,500,000. $866. How long would it take me to do that by hand or even with a calculator? With a computer, if you know how to write a for loop, step compile your code, make sure you get all the syntax right, I guess. What if I change it to equal 1,000? Plug in 1,000? Like, once you know this formula and get rid of the summation part, it's amazing how perfectly this works out. Any questions so far on that? Okay. Yes. So this starts at index 2. I really want to start at index 1, right? So what would it be if I plugged in 1 here? The 1 cubed plus 1? So I really want to say take this plus this. If I did that, it would be the same starting at 1. But can I just add this number? I've changed it, right? So if I add this, I also need to subtract it. So I want to put this term into this sum so I can start at index 1, add basically an extra term here. But if I add an extra term, I also need to subtract this value. Otherwise, I change the total value.
So, what exactly would change if
Start with index of 3. Let's say this was k equal 3. I'd subtract this sum k equal 1, 2 of k cubed plus 1. Or I would add and subtract it. Does that make sense? I want to start at 1, so start at 1, stop at 2. Those are all the terms I ignored when I started 3. So these are all the terms I skipped over, add them and subtract them. When I add them, it's the same as just putting a k equal 1 here. But then this minus tells me what I need to subtract to correct it. I think your question was more along the lines of this. But if I had something like that, if you said minus. Is that go through what you had in mind in that? Did I misunderstand it? Technically, it was when we just had this. So what would we do there?
Well, if you square it, you turn into a polynomial.
Could. Or I could treat this as 2 different sums.
Alright, but I meant you square.
This is without
And
squared. So without it squared, I would just break this apart.
Yeah, because I meant without the square, but then you asked when with the square, and
Yeah, with the square, what would I do?
that's.
You could expand it. Or get up. Alright. So instead of doing k-1 squared and relabeling my shift or index or anything like that, I could actually expand this out and I'd get this. Why would that be useful? Now, since everything was already at index 1, I keep that structure. I can write it as 3 different terms. But now I don't have this index issue. So like if I already have everything starting at k-1, I want to keep that. And then rewrite the inside part to make it all that. I don't have a formula for k-1 squared, but I do have a formula for each one of these 3 terms. So by writing it out that way, you can just use 3 formulas. There are other ways to do it. Because you can always play with your index and shift things around. Yes.
Okay, so you know the formulas for k equals 1, right?
Yes.
So it has to be in that form for us to be able to convert it to these formulas.
Yes.
And to switch it around, we can set it to k equals 1 and subtract what
we needed to add.
Subtract the difference. Doesn't that require you to, like, say you had k equals, it starts at k equals 1,000.
Yes.
Would you actually have to find the difference as it goes up there individually? And subtract that from what you
Yes, but
found?
you have to have a formula for it. So it's not as bad as it sounds. Because what happens here, when I said, so when you change this to 3, change it to 300. I would add and subtract this. But I have a formula for that because it starts with k-1. So I actually know a formula for what I'm adding and subtracting. So the subtraction part, I could write as a formula. The other part, when I'm adding it, just goes into here to make it k-1. So it sounds awful, but I can use the formula in 2 places. So it actually works out. It's because I'm adding something, subtracting something that starts at index 1. So I'm adding something I already know how to work with. Otherwise, yes, it sounds like you have to add together 299 terms to do this trick. That would be awful. It's almost more work than just doing it potentially. The catch is, this started at 300, I don't know what to do. But what I need to do to fix it, I actually know formulas for it. So it works out. All right. Any other questions? We always give you really easy notation and suddenly go a completely different direction than you have in mind. That's our goal, right? The reason is we care about the applications that come next. All right, so I want to do one more example today. Maybe the prep problem was misleading. Alright, let's find. Of course we're going to do this. Limit as n goes to infinity. The sine equal 1 to n. K plus 1 cubed divided by 3n to the 4. Why would we not add a limit? What's the point of this example? Or why would this maybe make sense to do something like this? Think about this one right here. We said you could do it for n equal to 100, right? Or you could do it for n equal to 1,000, or 10,000. What's our next question in calculus? If I can make n bigger and bigger, what happens when n goes to infinity? Does it add up to a number or not? So what would this one add up to? You had to guess.
Infinity.
Infinity? There's nothing, I keep adding bigger and bigger numbers forever, it's going to go to infinity. So then what happens in this problem? These get bigger and bigger, right? That goes to infinity. Well, what's the difference here? I'm going to divide by n to the fourth. This now has that form, infinity divided by infinity. If this number is big enough, so if n to the fourth is big enough compared to this number, there's a chance this actually adds up to a single value, which is crazy. There's a whole topic, you do it, especially in Count B. But the idea is you can add together infinitely many terms and you only get a finite number. Right? Even though they're all positive numbers, they're getting so small, close to zero, so fast that when you add them all together, you still basically just get a finite number. Yes?
I was actually gonna say, wouldn't the n on the bottom win since it has a bigger exponent?
Yeah, there's a reason I need n to the fourth. Otherwise it doesn't work out right. So like if I just did divide by n and not n to the fourth, I'd get infinity still. I need this to be big enough to counteract the fact that it's infinity. Okay. So like what does this look like? That'd be what? 2 cubed over 3 n to the 4. Plus 3 cubed over 3 n to the 4. Plus 4 cubed over 3 n to the 4. Plus my last one would be n plus 1 cubed over 3 n to the 4. Which you can't look at that and have any idea what it necessarily adds up to. But like this number technically goes to 0, doesn't it? I'll mess it up. N cubed divided by n to the 4th. The one on bottom wins. So that's an n to infinity. Same here. Technically, this number goes to 0. So I'm adding together infinitely many things, but they're getting smaller and smaller. And the question is, do they add up to something or not? If they do, that means I have a limit. If they don't add up to anything, I might not have a limit. Yes?
I just realized, why do we have k and n in like both like within the?
So this depends on n, this depends on k. And I can have both in here. Technically, this is the same as this. Why am I allowed to move the 3 into the 4th outside? Because it doesn't depend on k. I can factor it out of all these terms. These terms all depend on k, so I'm not allowed to move them. But n doesn't depend on k, so I could move it out here. I can't move it out here because it has to be inside the limit. So there is a way you can kind of split these up. Usually when we write the problem, they're all mixed together. Because that's what will show up when we do the applications. Right. What else can we do? Alright, so I was going to do this the long way. But we asked lots of questions, which is good. So instead, I'm going to do it a different way.
Wait.
Is that the same thing? Yes.
Technically speaking, so the 1 over 3 n to the 4th, that goes towards 0. So when like we take the limit, like, and that's 0, then multiply this the notation by 0, wouldn't we technically get
It's not 0 yet, because we haven't plugged in. I mean, it looks like 0 times infinity. That's really what
right?
But 0, I'm plugging in infinity here, this would be 0. This goes to infinity. 0 times infinity is indeterminate, which means we may or may not have a limit. We have to do more work. So we're going through the more work portion. All these end up being indeterminate when you have these. Is this believable? This starts at what? 2 cubed plus 3 cubed plus 4 cubed. So I could just start at 2, go to n plus 1.
Why wouldn't we just subtract 1 plus 1 cubed?
I wanted to k cubed by itself first. So now that I have k cubed, this is not what I had in mind doing this, but it's a shorter way to do it. What happens if I want to start at 1 and stop here? I would need to subtract when I plug in 1 cubed, because I was starting at 2 here. But then what else? It says add n plus 1 cubed. So because I left the last term off, I need to add it back. So like this one, I gained a term, I need to subtract it. I left off a term, I need to add it. The other way you could do this is I could expand k plus 1 cubed, which is k cubed plus 3k squared plus 3k plus 1. And just make it 4 different sums. I could have done that. So we're kind of doing this 2 ways. One second, I'm subtracting this. So what happens here? I know this stuff. What is it? N squared, n plus 1 squared, divided by 4. Minus 1 plus n plus 1 cubed. And then what's the last thing that happens? This is basically into the 4th term plus something. So you want to multiply this all out and check. But it looks like the limit is it goes to infinity of, what do I get for my highest order term here? N squared times n squared. Plus other ones, what do these other ones depend on? N cubed, n squared. So they're not the dominating power, right? So what happens for limits? I have n to the 4th over n to the 4th. So I just get 1/12 after the n to the 4ths go away. And then for the limit, all these, I get things like n cubed over n to the 4th. That'll go to 0. So it'd be a bunch of 0 terms when I take the limit. So my actual limit is the 1/12 value. Yes.
Where did you get the k equals 2 from?
K equal 2?
Yeah.
Oh. I need to start at, if I plug in 1 here, I start at 2, right?
Yeah.
So if I just write a k, that k has to start at the number 2.
Oh.
I did this the short way because I was running out of time. I could post the solution that's much longer. I'll post that in that.